Today we are going to see about theorem 1.2 in abstract control theory. Let f be the densely defined linear operator. If r of lambda a exists for all real lambda greater than or equal to lambda naught and limit lambda tends to 0 supremum of L lambda inverse log of r of lambda is to a less than or equal to 0, less than or equal to 0, then the initial value problem, initial condition is given here is d of u of t divided by d of t equal to a into u of t for t greater than 0, greater than time u of 0 equal to x, has at most one solution for every x belongs to, it must have a one solution. So proof means let a be the densely defined, it is densely defined operator already defined here. Note that u of t is a solution of 2, u of t is the solution for this, and if and only if we take v equal to e power zt u of t is the solution of the initial value problem, v is the solution of that initial value problem, we consider that, then what we do means dv by dt gives z into e power z of t u of t plus e power z of t into u dash of t. We already know that du by dt equal to a u of t, that is a u of t, e power z u taken as common means zi plus a, here a plus zi v of 0 equal to x. So thus we may translate a by a constant multiplier, we may translate this equation by a constant multiplier of constant multiple of identity. Okay, next constant multiple of identity. Next what we have to do means assume that r of lambda is to a exists for all real lambda, lambda greater than or equal to 0. If um, if if we assume that this one exists means it will already have that limit lambda tends to infinity supremum of lambda inverse of log is less than or equal to 0 must be satisfied. Okay, the initial value problem u of x equal to 0 has at most, if it has a solution means this should be satisfied. Okay, so let if it we have to assume this, we have to translate a by a constant multiplier identity, then we have to assume this, and we have to show that u of t equal to u of 0 has, it has at most one solution. So let u of t be the solution of 2, obviously we know that satisfying u of 0 equal to 0, and we have to prove that u of t equal to 0. We have to consider the function, that function from t to r of lambda is to a u of t for lambda, for all lambda greater than 0 their function must be from t to r of lambda a into u of t. Since we know that u of t is the solution of 2, definitely it's the derivative will definitely exist. So d by dt r of lambda is to a u of t means r of lambda a d by dt of u of t. U of t we already know that a u of t. We know that x belongs to domain of a means, that means dense of a means r of lambda I minus a x equal to x, and we take means equal to 0, this will be taken as lambda's outside, r of its identity map is nothing but constant multiplier of a, so lambda is to a of x minus r of lambda is to a of x minus x. Okay, we know that x equal to u of t, our solution is a form of u of t, so r lambda is to a into a u of t equal to lambda is to a u of t minus u of t. If we take the derivative, we know that the derivative form already exists, so r of lambda a u of t must be replaced by the lambda of r lambda a u of t minus u of t. So let us denote this is a long term, so for our simplification we take k of t equal to r of lambda is to a u of t, dk by dt equal to k in lambda into k of t minus u of t, dk by dt minus lambda k of t equal to minus u of t. To first order linear we have to multiply e power minus lambda t on whole then what we get means this is in the form of u dv uv math uv dash plus v u dash. So d by dt can be written as d by dt of e power minus lambda t k of t equal to minus e power minus lambda t u of t. So next what we do means we have to integrate from 0 to t. If we integrate means integrate and differentiation or getting cancel, substitute the upper limit minus lower limit means e power minus lambda t k of t minus e power 0 k of 0 equal to minus integral of 0 to t e power lambda tau. If we get an integrate means the variable changed to as a dummy variable, that is tau denoted here. Then we know that k of t equal to r of, because it's a constant, so for our simplification we take that k of t. So if we substitute means what we get means r of lambda is to a u of t e power minus lambda t equal to minus 0 to t e power minus lambda tau u of tau d tau. So this is goes to this side, so t minus taking lambda as common means t minus tau u tau of t, multiply both side by e power minus sigma lambda for every sigma greater than 0. So e power minus sigma, that is r of lambda is to a u of t equal to minus 0 to lambda 0 to t e power lambda t minus tau t minus here minus sigma u of tau d tau. So the assumption 1, it follows for every assumption 1, that is nothing but limit supremum lambda inverse of log r of lambda is to a less than or equal to 0. No, that assumption follows for every sigma greater than 0. So limit lambda tends to 0 e power minus sigma r of lambda is to a equal to 0. So therefore it follows from 4. What is the 4 mentioned here? This one, r of lambda u of t can be written as this form. R of lambda lambda a can be written as this form. So substitute here, limit e power limit lambda tends to 0 to t e power lambda t minus sigma minus tau u of tau d tau. If it is from assumption it is 0, so we from 4 we assume that this is also 0. If we take the limit outside means we get the norm of m, norm value less than or equal to m. So from our lemma what we know means if u of t be a continuous x valued function on 0 to t, if integral value 0 to t e power ns u of s ds less than or equal to m. If it is less than or equal to m means what we do means, if it is less than or equal to m, then u of t equal to 0 on 0 comma t. On that 0 comma t u of t will be 0. So we deduce u of tau, we deduce that u of t will be definitely 0 for 0 less than or equal to t less than or equal to t minus. Since t and tau are arbitrary and we definitely choose that u of t equal to 0 for all t greater than or equal to 0. So this is only we have to prove that we proved. Hope you all understand and thank you.